Hi everyone, welcome back to 3.4 and 3.5. So, little break there where I was in the flush for 3.3, but now we're back digitally. At least I can beat that. I'm not an AI allegation. So, with that said, we're going to get into 3.4. However, 3.4 and 3.5 separately discuss the real and complex zeros of a polynomial function. Personally, I think it helps a little bit better with the flow if we treat it all as one big section. But just so you know that if you're using this textbook, there are two separate sections. I think it's just easier to talk about everything all at once. So we're going to work our way up to the fundamental theorem of algebra. So if you're watching this, you might be in an algebra course, you might be in a pre-calculus course. So it's very interesting because fundamental theorem of algebra is the fundamental theorem of algebra, right? It's going to hold together a lot of the things that you talk about in your class. So with that importance in mind, let's keep it going. So let's start with the rational zeros theorem. Now, the rational zeros theorem is just this quirky little thing that's actually pretty nice from what we just did in 3.3 with polynomial long division. But what it says is this. If a polynomial has integer coefficients, which in a lot of cases it will, and P over Q is a rational number, that is a zero of P of X, then P is a factor of the constant term and Q is a factor of the leading coefficient. Now, that's very wordy. Long story short, you take factors of the constant term and divide them by factors of the leading coefficient. What you get is a set of all possible rational zeros. Not a comprehensive list of all zeros, since some zeros can be irrational, like zeros you can get from the quadratic formula, but it is a list of all rational zeros that will appear in your function. So for example, if your function has a rational zero, it will appear in this list, but it just won't be a list of all of them. And you're also going to get plenty of other ones that are not zeros either. So what we're going to do is take each potential zero in our list, use synthetic division to very quickly check to see if it is a zero, and then help us factor from there. So we're not going to do that part. We're going to skip over that, right? We saw that we had to do an entire board presentation just for that. But we can take the steps for granted here. So let's start by finding all the rational zeros of 2x cubed plus 5x squared minus 4x minus 3. Okay, so how we do this is we look at the constant term and we look at the leading coefficient. The constant term is negative 3. And the factors of negative 3 would be 1 and 3, and plus and minus 1 and plus and minus 3. So here are the factors of negative 3. And then the leading coefficient is 2. And likewise, its factors are plus and minus 1, plus and minus 2, right? These are not so scary, but think about something like 6. That might be 1, 2, 3, and 6. Okay, so the set of all possible real rational zeros is given by plus or minus 1, plus or minus 3, factors of the constant divided by factors of the leading coefficient. Now, just for the sake of redundancy, we can drop the plus and minuses in the bottom. And this right here, even though not the most mathematically perfect way of writing it, this would generate all of the possible real rational zeros for our function. So if we wanted to write that actual set, it's as follows: positive 1 divided by 1, negative 1 divided by 1, positive 3 divided by 1, negative 3 divided by 1, positive 1 divided by 2, negative 1 divided by 2, positive 3 divided by 2, and negative 3 divided by 2. Had we left the plus and minuses in the bottom, what you would get is just plenty of zeros that repeat. So save yourself a little bit of work and don't put any pluses and minuses in the denominator. Okay, so now we have a set of all possible rational zeros. Not all of them are going to be zeros, obviously, right? This is too many. Here's 8 possible zeros, but we're only degree 3. There's no way that all of them could work. So what you would then do is check each one using synthetic division. However, once you check each one using synthetic division, once you find a zero, you can factor that result based on that zero. So here's what I mean. If we know that x equals 1 is a zero, well, do synthetic division using x equals 1, and you would get x minus 1 times 2x squared plus 7x plus 3. Please go back and check the 3.3 presentation to see how exactly we would get that. But essentially, x equals 1 works, so our function can factor like this. Now, the really nice thing about this, too, is that this is also factorable. Okay, well, think about it this way. I mentioned in 3.3 that polynomial division can help us go from something that can't be factored using regular methods to something that can be factored using after using long division. For example, try factoring this using anything we've talked about in the past, and you can't. But polynomial long division brought us to a point where it is factorable, right? These factors are very nice and pretty, but we needed long division to do that. So it is a tool to factor. Okay, just to summarize 3.3. But now, if we want to find all the rational zeros, well, now just set all of these equal to 0, and we would get x equals 1, x equals -3, and x equals -1/2. Degree 3, 3 zeros, nothing missing, and here's one more interesting part about rational zeros theorem. All three of these zeros did appear in that list that we just had. So we got 5 other zeros that were not true, but all the zeros that are here, all these rational zeros, did appear in that list. We just happened to use x equals 1 as our starting point to do long division. But you could have done the exact same thing with x plus 3. You could have done the same thing with 2x plus 1. So rational zeros theorem says we have a way of getting all the possible rational zeros. Well, you might find this is a little inefficient for an example like this one. Your constant term is 8. So the factors of 8 are 1, 2, 4, and 8. And then your leading coefficient is 3, whose factors are 1 and 3. So the set of all possible real rational zeros would be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8 over 1, 3. Again, take the constant factors, divide them by the leading coefficient factors. And now the set of all these zeros is a lot longer. So this is not fun. So the point here is that the rational zeros theorem only gives us a set of possible zeros, not a very necessarily useful set. So you would have to go through and check all of these. So part of the reason why rational zeros theorem isn't super useful is that you could be spending a lot of time to find a rational zero that might not actually even be a zero, right? This is a set of possible rational zeros. What if your function doesn't have any rational zeros to begin with? So we'll take for granted that we will check each using synthetic division. And again, once we find a zero, factor that result. So let's just say that we knew that 2/3 was a zero. Well, knowing that 2/3 is a zero, then we would get something like this. We could factor this by taking out a 3. And then to find the remaining zeros, well, we would need to do quadratic formula on that. So in total, all of our zeros of our function would be 2/3, and after doing quadratic formula, 1 plus and minus square root of 5. So, it would have taken you a long time just to get to 2/3. But again, the point here is that we went from something that you could not find the zeros for to something that we could find the zeros for, even if not that pretty. So that's just a lead in to the point that we actually want to look at, and that's the fundamental theorem of algebra. Okay, if your polynomial is degree n, it has at most n real zeros. We looked at that in 3.2. In 3.2, we said, we would have a degree 3 polynomial, but we would only have like 2 zeros. So like what happened? Multiplicity describes some of that, but what we're going to do here in 3.4 and 5 is perfectly describe that. Okay, but also don't forget that all real numbers are also complex numbers. Oh, It's been a long time since we've talked about complex numbers, just numbers that may contain I. So what happens if you have a degree 10 polynomial that has only 4 real zeros? Where are the other 6? Well, we saw in the last, in 3.2, that you could have multiplicity describe some of it, but not always all the time perfectly describe it. So that brings us to the fundamental theorem of algebra. Every polynomial function like this of degree n greater than or equal to 1 has at least one complex zero. So don't forget, real numbers are also complex numbers. So just because it has at least one complex zero doesn't necessarily mean it has an imaginary zero, right? Real numbers, 2, 5, -3/2, those are all real numbers. Fundamental theorem of algebra says we have at least one complex zero. But the main result of fundamental theorem of algebra isn't necessarily that part. It is factorization theorem. Factorization theorem says that all polynomials of degree at least 1 can be factored as this. P of x equals a sub n, x minus c1 times x minus c2, all the way to times x minus cn. A sub n is the leading coefficient, and ci are just non-distinct complex zero factors of p of x. Okay, that's really, really interesting. Every polynomial can be factored. Maybe the factors necessarily aren't super pretty, but it can be factored. So going back to this, we say those zeros are non-distinct because, for example, you can have a degree 7 polynomial that looks like this. And we actually described this in 3.2, where we had the possibility that like only 3 zeros for a degree 4 polynomial, but the multiplicities of those 3 add to 4. So that's kind of what's happening here. Point is, those zeros, those factors, don't need to be distinct. Okay. Then, if every polynomial has at most n real zeros and at least one complex zero, then every polynomial of degree n has exactly n complex zeros. Well, that is, if you include multiplicity, if you include irrational zeros like you could get from quadratic formula, if you include imaginary zeros, every polynomial has exactly n complex zeros. So before, we had a degree 10 polynomial and we said it only had 4 real zeros. Where are the other 6? Well, they're imaginary. Okay, degree 5 polynomial with only 3 real zeros has 2 more complex zeros. A degree 12 polynomial with only 8 real zeros has 4 more complex zeros. And I'm not going to gush like crazy. Normally, when I'm talking about this in person, I get very animated. That's just what the in-person lectures look like. But I get really animated to the point that I'm like, this is really, really important. It holds the study of algebra together. How do you have the fundamental theorem of algebra, or how do you not have the fundamental theorem of algebra and be able to do anything that we've done in this course together? So whether or not you're watching my videos because you're in one of my 16-week classes, whether or not you're watching my video because you're in my 3-week classes, whether or not you're watching my video because you're in some other class, everything you've learned in algebra and almost all of mathematics can't be held together without the fundamental theorem of algebra. So that's my little bit of online gushing. So that brings us to 2 more theorems that we need before we actually start to apply these things. Conjugate pairs theorem says this. If you have a polynomial that has x equals a plus b squared of c, that's an irrational zero of the polynomial. Then x equals a minus b squared of c is also a zero. That is, all irrational zeros come in conjugate pairs. A plus b squared of c is a zero, then a minus b squared of c is a zero. Well, if x equals square root of 5 is a zero, then x equals negative square root of 5 is a zero. If x equals 11 plus square root of 20 is a zero, then x equals 11 minus square root of 20 is a zero. If x equals negative 8 minus square root of 13, then x equals negative 8 plus square root of 13 is a 0. If x equals 2 plus 2 square root of 2 is a 0 with multiplicity 5, then x equals 2 minus 2 square root of 2 is a 0, also with multiplicity 5. And this is a perfect example as to why quadratic formula always gives 2 zeros when your discriminant doesn't equal 0. For example, in that second example we did for rational zeros theorem, the two other zeros to the function were 1 plus square root of 5 and 1 minus square root of 5 via quadratic formula. So this is why quadratic formula always gives a pair of zeros, not only when it's irrational, but also when it's rational and real. Okay, well, we also have another conjugate pairs theorem that's very similar. If you have an imaginary zero, a plus bi, then x equals a minus bi is also. This should say complex. That's a mistake. If a plus bi is a complex zero, then a minus bi is also a complex zero. That's my bad. So if x equals positive I is a 0, then x equals negative I is a 0. If x equals 11 plus 20i is a 0, then x equals 11 minus 20i is a 0. If x equals negative 8 minus 13i is a 0, then x equals negative 8 plus 13i is a 0. If x equals 2 plus 2i is a 0 with multiplicity 5, then x equals 2 minus 2i is also a 0 with multiplicity 5. So when quadratic formula has two imaginary answers, it's always why there's two imaginary answers when the discriminant is less than 0. So all of this kind of coming back to 1.3 when we initially learned quadratic formula. Okay, so let's just practice finding some missing zeros, but what we eventually want to do is construct polynomials, which is a lot more interesting. Okay, so let's say our polynomial is degree 5, and its zeros are 6, negative 4 plus 3i, and 2 minus square root of 7. I gave you 3 zeros, but we're degree 5. We are missing 2 zeros. Well, negative 4 plus 3i is a 0, so negative 4 minus 3i is also a 0. 2 minus square root of 7 is a 0, so 2 plus square root of 7 is also a 0. So in total, I gave you 3. We found 2 more, all 5 zeros right there for us. Okay, let's say we have a degree 10 polynomial and it has zeros negative 10, 0, negative 1 minus 2i, 2 minus 3i, square root of 15, and 1 plus 5 square root of 2. I gave you 1, 2, 3, 4, 5, and 6. Well, degree 10, I give you 6 zeros. We're missing 4 zeros. Because negative 1 minus 2i is a 0, negative 1 plus 2i is a 0. Because 2 minus 3i is a 0, 2 plus 3i is a 0. Because positive square root of 15 is a 0, negative square root of 15 is a 0. Because 1 plus 5 square root of 2 is a 0, 1 minus 5 square root of 2 is also a 0. And then we had 6 zeros to start. We found 4 more, all 10 zeros right there. Okay. Well, let's do, I think, one more example of this. Degree 17. The zeros are 2 multiplicity 3, 4 plus 5i multiplicity 2, 3 minus square root of 10 multiplicity 5, and let's find the remaining zeros. Well, I gave you 3 plus 2 is 5, 5 plus 5 is 10, so including multiplicities, 10 zeros, but we're degree 17, so we're missing 7. 4 plus 5i is a 0 with multiplicity 2, so 4 minus 5i is a 0 with multiplicity also 2. 3 minus square root of 10 is a 0 with multiplicity 5, so then x equals 3 plus square root of 10 is also a 0 with multiplicity 5. So then we had 10 zeros to start, and we found 2 and 5 more, including multiplicities. How lovely, how nice. Okay, well, that brings us to constructing polynomials, and this definitely the wrap up to the course. Unfortunately, it doesn't end on such a beautiful storybook note. We have one more section at the end, but this is really, really the key to algebra, to any algebra class. So Find a polynomial of degree 3 that has leading coefficient 1 and these zeros. Well, this comes back to factorization theorem. What we're normally used to doing is starting with a polynomial and then, finding the zeros. But what we can now do is construct polynomials given zeros. So the information that we're given is that our polynomial is degree 3, our leading coefficient, and we have 3 zeros. So what we're going to use is factorization theorem. Now, specifically, since we're degree 3, we're only going to go up to x minus c1, x minus c2, x minus c3. And now, let's just plug in the information that we have. The leading coefficient is 1. Our first zero is -2. Our second zero is 3. And our third zero is 7. So leading coefficient 1, first zero is -2, second zero is 3, third zero is 7, and we can simplify x minus -2 to x plus 2. We also don't need this 1 out in front. So this would be the perfectly factored version of a polynomial that fits this criteria. However, we know how to FOIL. We've practiced FOILing in the past, and we would get this, right? So chapter P stuff to FOIL, I don't want to go over that here. If you need help, by all means, go back to that, or just use an online calculator. I didn't say that out loud. Okay, anyway, so we have the polynomial that fits this criteria. Okay, degree 2, leading coefficient -1, and zeros -4 and 0. Okay, so factorization theorem says this, but since we're degree 2, we're only going to go up to x minus c2. Well, our leading coefficient is -1, our first zero is -4, and our second zero is 0. All right, well, x minus -4, x plus 4, x minus 0 is just x, and if we ever have just plain x's, we like to write them in front. So we get -x, x plus 4, and you can distribute -x to get the polynomial that does this. So all it is, plugging and chugging, and then in some cases a lot of foiling, but we don't need to do the foiling here. Okay. Degree 4, leading coefficient 1 with zeros 0, 2, 5, and 10. Okay, well, if we're degree 4, we're going up to x minus c4. Our leading coefficient is 1. Our first zero is 0. Second zero is 2. Third zero is 5. Fourth zero is 10. All right, well, x minus 0 is just x. And this nice factored version, but we can practice our foiling. So these are the best examples to a fundamental theorem of algebra, just using the result of the factorization theorem. Okay, leading coefficient 3, degree 4, with zeros -5, -1, 2, and 6. All right, well, degree 4, go up to C4. Leading coefficient is 3. Our first zero is -5. Second zero is -1. Third zero is 2. Fourth zero is 6. We can simplify x minus -5 and x minus -1. And, now that we've done a couple examples, I just want to throw out there that this is usually a pretty nice form. If you can get to this point, you really learned the course. And as you see the next couple examples, it's only going to get worse when it comes to foiling, right? Foiling out 4 things is no fun by any stretch of the imagination. So again, the stuff to take away here is really getting up to this point where, we have a polynomial that equals this thing. But the point is that even if you don't know how it factors, it does factor one way or another. Okay, let's start to introduce some imaginary zeros, right? We said some weird stuff about irrational zeros, about imaginary zeros. So let's put that into here. Okay, well, polynomial is degree 4. Our leading coefficient is 2. Our first zero is -1, then 3, then I, then -I. Okay, let's simplify our negative negatives. And we get a perfectly factored polynomial. So this is what it is when you expand it, right? Practice your foiling. This would be a 1.4 practice. P3, foiling regular polynomials. But in 1.4, we practice doing that with I. So go back to 1.4 if you need help with that. But point is that this can be factored if we allow our zeros to be i's. And zeros are i's, and even though we never wrote stuff like this in the past, it doesn't change the fact that this is, say, a factor of our polynomial. So something to keep in mind. All right, degree 3, leading coefficient 1, 2, 1 plus 3i, 1 minus 3i. Degree 3, leading coefficient is 1. First zero is 2. Second zero is 1 plus 3i. Third zero is 1 minus 3i. So a little uglier now, but here make sure you distribute a negative sign to both, and make sure you distribute a negative sign to both. This nice factored version, and you already start to see how crazy this could get. So yeah, be careful about that. But again, it's all really just plugging and chugging. But what we can now introduce is that you don't necessarily need to be given all the zeros to solve these types of questions. So degree 3, but I'm telling you only 2 of the zeros. Specifically, I am telling you only 2 of the zeros. So degree 3, leading coefficient is 1. First zero is -1. Second zero is 2 plus 2i. But notice that we have a factor that we haven't filled in yet. Well, don't forget that if 2 plus 2i is a 0, then 2 minus 2i is also a 0. So I can omit information, and you could still find that information the exact same way. Okay? So minus minus, distributing negative signs we get here. And yeah, maybe this answer doesn't look so bad, but when you go to FOIL something out like this that's got 3 parts each, it's not pretty. So definitely practice doing that. Okay. Degree 4, leading coefficient 1 with zeros 0, 4, and 1 minus I. Again, degree 4, but I only give you 3 zeros. Okay, well, here's degree 4. Leading coefficient is 1. First zero is 0. Second zero is 4. Third zero is 1 minus I. But don't forget that if 1 minus I is a 0, then 1 plus I is a 0. So the first few examples, I gave you both parts in the pair, but I don't always have to do that. Here, I can just give you 1 minus I, and you find the other one. However, I could also just give you both in the pair. So I can go both ways. Let's distribute negative signs here. X minus 0 is x. 1 times x is just x. This is a nice, pretty answer. And there it is after you FOIL. Okay. Degree 3, leading coefficient 4 with zeros 1 and 2i. So degree 3, leading coefficient is 4. First zero is 1. Second zero is 2i. And then our missing 0 is -2i. Okay, and there we go. Degree 3, leading coefficient -2. 0 is -1, -3i. Well, degree 3, leading coefficient is -2. First zero is -1. Second zero is -3i. But if -3i is a 0, then +3i is also a 0. Distribute some negative signs, and then FOIL. Lots of foiling. I know I'm skipping through all of that, but I think by now, if we're talking about factorization theorem and fundamental theorem of algebra, that the foiling part is very much deep-rooted into our minds. Okay, degree 3. Well, let's start to introduce some irrational zeros like square root of 7. All right, well, they function almost exactly like i's. If anything, they're a little bit nicer to evaluate when you are foiling. Okay, degree 3, leading coefficient is 1. First zero is 3. Second zero is square root of 7. Third zero is negative square root of 7. Distribute that negative, and now we get here. Okay. Well, we can very quickly change this to me only giving you one of the irrational zeros. So degree 3, leading coefficient 1, zeros 2, and square root of 3. I only gave you two of them. You can find the third one. Degree 3, leading coefficient is 1. First zero is 2. Second zero is square root of 3. But if positive square root of 3 is a 0, then negative square root of 3 is a 0. And then we are rinsing and repeating. Okay. Polynomial of degree 5 with leading coefficient 1 with zeros 2 and negative 5, each with respective multiplicities of 3 and 2. So here's how we could set this up. If we're degree 5, we got to have 5 factors. Our leading coefficient is 1. Our first 0 is 2, but we have 2 3 times. Then our next 0 is negative 5, but negative 5 multiplicity 2. Well, we can simplify this right away to be x minus 2 cubed and x plus 5 squared. So when you're going to set this up, if you were to show me work, right, if we're doing like physical assignments, you wouldn't need to show me doing this step if you can jump right to here, right? Given just this information, you probably could have jumped to what the answer was going backwards. But my point is if you are comfortable jumping right to an exponent version of the factored form, that's totally fine too. I wouldn't have a freak out about that. But then, maybe now things will start to look a little ugly in our functions. But again, multiplicity, not changing a whole lot, just adding some exponents. Okay, degree 10, leading coefficient 1, x with zeros, x equals 0, multiplicity 2, x equals 1, multiplicity 5, x equals negative 6. No multiplicity said, so we assume it's multiplicity 1, and x equals 2, multiplicity 2. So here's a great example as to why we wouldn't write out all 10 zeros. For x equals 0, multiplicity 2, we'll do x minus 0 squared. For x equals 1, multiplicity 5, x minus 1 to the 5th. For x equals negative 6, just x minus negative 6. And x equals 2, multiplicity 2, x minus 2 squared. You would be very welcome to write out all 10 zeros if that helps you, but I think you'll find it's very tedious to be writing out something that long when you could just be using exponents. Here's a nice simplified version, and either practice foiling or enlist the help of an online resource. Okay. Degree 7, leading coefficient negative 5 with the following zeros: negative 2, 1 multiplicity 2, and 1 plus I multiplicity 2. All right, so we are degree 7. Our leading coefficient is negative 5. Our first 0 is negative 2. Our second 0 is 1 multiplicity 2. Our next 0 is 1 plus I multiplicity 2. But don't forget that if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity, right? I gave you 1, 2, 3, 4, 5 zeros to start, but we were degree 7, so we knew that we were missing 2 zeros. And that came in the form of just one more factor with a squared. All right, distribute some negatives, simplify that. And yeah, these are getting even better by the slide. All right. Degree 7, leading coefficient 17 with zeros: negative 5 multiplicity 2, 0 multiplicity 3, 5 multiplicity 2, and 23i. All right, degree 7, we have leading coefficient is 7. We have x equals negative 5 multiplicity 2, so we'll throw a squared there. X equals 0 multiplicity 3, so x minus 0 cubed. X equals 5 multiplicity 2. Then we get x minus 23i, but don't forget that if positive 23i is a 0, then negative 23i is also a 0. Simplify a little bit, and yeah, you all definitely knew 5,620,625, right? No problem at all. Okay, degree 10, leading coefficient 1, x equals 1 plus I multiplicity 2, and square root of 3 multiplicity 3. I gave you 2 zeros plus 3 zeros for a total of 5. So if we're degree 10, we're missing 5 zeros. Okay, well, we have 1 plus I multiplicity 2. So this is x minus 1 plus I squared. But if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity. Well, we have x minus square root of 3, multiplicity 3, so cubed. If x equals square root of 3 is a 0, then x equals negative square root of 3 is also a 0. Okay, simplifying some negative signs, and we get this monstrosity that I would never expect somebody to actually do in person. But there we go. All righty, we're nearing the end, but we continue. All right, leading coefficient negative 57 with zeros 3 plus 7i, multiplicity 3, negative 4 plus 6i, multiplicity 3. So we would have negative 57 leading coefficient. Our first zero is 3 plus 7i 3 times. Well, if 3 plus 7i is a 0, then 3 minus 7i is a 0 3 times. If negative 4 plus 6i is a 0 3 times, then negative 4 minus 6i is a 0 3 times. Okay, this is fun. This polynomial, I think I tried plugging this into an online resource, and it just wouldn't give me an answer back. It said it was too big. So, as we get a little crazier, I would never expect you to fully expand it, but especially getting up to this point is definitely the key new part to this section. And that brings us to the end of 3.4, 3.5. So normally that would be a really nice storybook to end with, like, this is the fundamental theorem of algebra, but we have one more section that is still in a, not necessarily in the progression of quadratics to polynomials to real and complex zeros, but rational functions still important enough for us to talk about. So we'll do that in 3.6 for the final section of this algebra course and these algebra videos that you have been watching. So until then, I will see you in 3.6. Bye. Hi, everyone. Thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition, by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.